actually. It is still small, 1 millivolt. But what if we are using an integrator? Do you remember this circuit is an integrator? We used to have the input here. It is not still like an inverting op-amp, right? And the gain is related, if you go to the frequency domain, the impedance of this divided by the impedance of this, right? And then we say we do the Laplace transformation. We show that this is an integrator, right? Remember this? What if you have an offset? If you have offset, this part is ideal, right? This part is still ideal. But the real op-amp that you have has this whole part. This is the real one that you have. Why we have this VOS? Because we already say that it has offset, and we decided to model it as a voltage source attached to the plus terminal. This is a voltage source attached to the plus terminal, right? And we ground it because in this setup, we ground the positive terminal, right? Okay, so the actual circuit you have in the integrator is this. Now, the question is, what happens if I have input equal to 0, right? If you have the V in equal to 0, I expect V out equal to 0 because you're integrating 0 input, right? The input is 0, you do the integration, the output should be 0 if it is ideal. But unfortunately, now we have this VOS. Then, what is the output? Now, we can derive it by looking at it in another way, right? So when V in equal to 0, and then with the VOS, the setup, this is just like a non-inverting amplifier. Right? With VOS as the input. Right? Because now I am studying if my real input is 0, what happened to the output? Isn't that it's just like I have an input at here, but it is VOS, it's constant, right? But I ground this terminal, right? So this becomes a non-inverting amplifier if I want to calculate the output. Is that okay? Right? Before, if I have ideal op-amp, this one is grounded, and I put input to here to do the integration of my circuit, right? And that is a inverting amplifier, and I get the transfer function. I find that it is an integrator. But now I just want to see, what if my input is 0 and I have an offset here? What will be the output? Now it's just like that. This is a non-inverting amplifier with the input offset, VOS, right? So because of this, then I know the output. I use the Laplace, I use the time domain. The output must be equals to the 1 plus ZC1 divided by ZR1, because this is the gain of the non-inverting amplifier times VOS, right? Look at this. The gain of the non-inverting amplifier is 1 plus R1 divided by R2, right? That is why I have 1 plus ZC1 divided by ZR1, because when I'm studying the effect of the offset on the output, it becomes a non-inverting amplifier. Is that okay? So this is another way, right, that we always say you learn how to map the circuit to what you have already learned. We already learned how to solve non-inverting amplifier. Now I want to solve this problem. I successfully map this to a non-inverting amplifier. And indeed it is, because output is here, input is here, this is grounded, Although your original purpose is to put input here, but now I ground it, right? So to solve this from here to here is non-inverting amplifier. Okay? Now, with this, then I will do some simplification. First of all, this one is equal to 1 plus 1 over SC1R1. Yeah, because the impedance of ZC1 is 1 over SC1, right? We studied last time. So this is the what we have. Now, another thing I want to do is I will assume this is approximately equal to VOS divided by SC1R1. Okay? Because VOS is a very small number, 1 microvolt, right? So I just assume this one, it is small. We can show that later, but I will just do this directly, okay? Not go into the details. Then what do? Do you remember? This is the frequency domain. So I'm going to do an inverse Laplace transformation. Yeah. When by definition, the output in the time is V out of t. How about the output on the right-hand side? Well, it is something divided by S. And this VOS is constant because it's the offset due to the process fabrication, right? So it's 1 microvolt forever, right? At least in our approximation. So in that case, this is just equals to 1 over C1R1. You integrate the constant VOS dt. Yeah, because something divided by S becomes integrating that thing. Although this time this thing is a constant, which give me VOS divided by R1C1 times T. Okay, now this is math. I don't really require you to be able to do all this in your exam. So don't worry about this, but I do want you to understand, because you understand this will help your future tasks. The point here is that you see the output depends on time. It goes up linearly. My input is 0, but because of this offset, the output keep going up, eventually hits the VDD. Then this integrator is completely useless, right? The goal is to integrate my signal. When I don't have signal, I expect the output to be 0. But I wait for a while, it tells me that the integrator value is VDD. Fail, right? So that is the biggest problem of the offset. Even it is tiny, only 1 microvolt. For example, in this case, not a big deal, right? I just amplify by 1,000 times, become 1 millivolt. Maybe my signal is 0.5 volts. I still get enough signal to noise ratio. But this one is really bad. It keeps integrating my offset voltage. Okay, is this clear? Yeah. So as an engineer, we don't only try to understand the problem, we will also try to solve the problem, right? So this slide will be a little bit difficult, but let's go through the process because it's a very important thing to help us to understand some important details. So people came up with this solution. We can discuss a little bit later how they came up with this solution. The solution is this. They're going to add a resistor R2 in parallel with C1, right? This was the original circuit, right? You see that we have the capacitor connecting V out to minus. What we do is we just make a resistor in parallel with C1, okay? And then we claim that this will solve the problem. Let's see if it will solve the problem. Now, first of all, let's look at this situation again. The first situation is that when my input is 0, I really hope that my output is small. I don't want it to keep integrating and becomes VDD, right? Because that screws up my solution. So if my input is 0, I hope it's 0. Now let's see with this resistor how it is going to affect the result. So at V in equals 0, what is V out? First of all, when we we will because this is 0 and because VOS is DC, is a constant voltage, right? So you have constant voltage. So because this is just a DC problem, right? When V in equals to 0, when V in equal to 0, this is just DC problem. There's no AC, right? What happened to capacitor 1? Is it important when it is DC? It is what? Open, right? So this becomes a very simple problem. This is just the V out just equal to 1 plus R2 divided by R1 times VOS, right? Here, when it is not DC and it doesn't have the resistor, we say that the V out equal to 1 plus this impedance divided by this impedance, right? Times VOS. But now, because when we're considering the DC issue, since we added the R2, it becomes V out times 1 plus R2 divided by R1 times VOS. So, okay? So if we make R1 much larger than R2, then V out will be similar to VOS, which is small. Right? Because when I pick a R1, which is small, much smaller than R1, I pick a R2, which is much smaller than R1, isn't that this term will become about 1, right? Because R2 may be 10 ohm, R1 may be 1 kilo ohm, then this is 1 over 100, this is 1.01. So V out is approximately equal to VOS, right? So I do solve the problem, the DC problem. I solve because if I didn't have R2, this will be the output. You will just keep integrating up. But because I have this R2, now it will just stay at about the VOS, a very small value. Okay? Looks like I solved the problem. But no, it looks like I solved the problem because I solved the DC problem. But is this still an integrator? I added the R2 already, right? I might change the whole thing. And now, how did people came up with this idea? That's why the insight is important. Remember how we did integration? The integration was because you keep charging the C1, right? Now, when you have a virtual ground, this is VOS. You expect this point is also VOS, right? At the minus, the virtual short, I'm sorry. So if this is VOS, then you have current going from this point to this point, right? Because VOS to the ground through R1. So you must have current keep going from here, right? Then you keep charging up the capacitor. And as a result, your V out keep going up. That's the problem of the VOS, right? Now, that's why people came up with this idea. That's what I guess, right? I did not read any original paper. If you can short this one with a resistor, then you are not going to charge up the C1 because the current can just go through here. And your V out will have a finite value. You won't keep charging up. If you don't have R2, this current will keep charging or discharging C1. That's why you get V out. Right? So that is another way to show that if we did not really try to understand what happened to the op-amp in the integrator before, you would not be able to propose the solution to add the R2. Right? Again, the reason I know that adding R2 will help is because due to virtual short, this is VOS. The current, there will be current going from here to through R1. And this current must go through the C1. And as a result, you keep charging C1. Okay. Now with R2, I bypass the current. So the V out will not keep going up. But however, when I add R2, is this still an integrator? Now I need to check, right? Is this still integrator? But this time you check, what if V in is not zero? Not zero meaning that you also have other frequency, right? So what is the gain? Now I'm going to ignore the VOS when we do this. We go back to the inverting amplifier. I know that V out of S equal to negative R2 parallel 1 over SC1 divided by R1 times V in. Anyone want to tell me how I get this equation? Yeah.
The top is the C, that's section C, let's call it C1 or C2 divided by C2.
Exactly. This is an inverting amplifier, right? Good point, because this is an inverting amplifier. I do not have the equation here. So this is an inverting amplifier. And you remember inverting amplifier is negative this impedance divided by this impedance. Again, I map it to what I have learned. I don't need to rederive it. That's why you need to understand those well. So this impedance then, you know, is just parallel. R2 parallel 1 over SC1, right? Because 1 over SC1 is the impedance of this capacitor divided by R1. Okay? Then I'm going to do some math. To save time, I just give you the result actually. It becomes R2 divided by R1 times 1 over 1 plus SC1 R1 R2 actually. Oh, actually it's on the times V in S. Okay. So after adding R2, the transfer function becomes this. Is this an integrator? Maybe you forgot, but I copy here. An integrator should have in the frequency domain with this form, V in divided by S. That is an integrator. Is this in the form of something divided by S? Is it? Something divided by S, purely S. No, right? Because you have 1 plus here. So it's not a perfect integrator. Very good point. Okay, because only with 1 divided by S would you get this integration in the time domain. If you have 1 divided by 1 plus something S, after you do the inverse Laplace transformation, you won't get this perfect integration. This is just math. Okay? Now, engineer comes to rescue again. How can you make this look like a good integrator then? What can you do? Is it find the zero and pose and? Okay, so basically what he say is find the zero and pose and then find a frequency so that the pose does not matter, right? So in other words, choose the R2 and C1 such that 1 doesn't matter, correct? If 1 plus R2 C1S is approximately equal to R2 C1S, isn't that this becomes an integrator, right? So that means I need R2 C1S to be much larger than 1, right? If this is really large, yes, this is not a perfect integrator, but only the science people will care about this because it's not, exactly not an integrator by definition. But as an engineer, this is so small. If this is 1,000, right? If the frequency you are interested in is 1,000, give you the whole thing 1,000. This one has no effect, has very tiny effect, right? So if I can do this, if I can make R2 much larger than 1 over SC1, and that's why this is related to the pole you set, right? I need to pick the frequency or whatever, or change the pole or change the frequency. Then this is a good integrator. Do you see that? So we do solve the problem, but not at every frequency. At certain frequency, it will fail, right? So as a summary, we want first R1 to be much larger than R2. Then you say, let me just pick R2 equals 0. I solve the problem, right? This is the 1. But then it's no longer integrated, because if R2 is 0, this is just a short, right? It's no longer a useful integrator. And that's why your R2 cannot be too small. It needs to be larger than 1 over SC1, which depends on the frequency you want to operate. So with this, we solve the problem of the offset in the integrator, right? Now, a lot of stuff here, but I feel that maybe this is the most difficult part in this whole class, which I'm not going to test really, but we have this in the assignment. But I hope you can think carefully about all this reasoning. And this is the exercise you are going to repeat in all your future engineering project in your work. Find the problem, understand the problem. Right? So find the problem means that when input is 0, output goes to VDD. And then understand the problem. Why we have this problem? Well, because you have offset, so this has offset. This offset create a current, and this is going to charge up the capacitor, so Vout go up. Understand the problem, then you try to solve the problem, propose idea. Okay, I just short this guy, then I'm not going to charge up the capacitor because the current can go through here, right? Then my Vout won't be high. And then evaluate your solution. Well, yeah, you solve the problem, but is this still an integrator? But the most important thing is accept imperfection. Yes, mine doesn't work. It's not perfect. However, I know that if I make R2 larger than 1 over SC, it will work as long as the customer only interested in this frequency. We can still sell this amplifier. If not, reiterate, right? This goes from the basic design even up to how to form a company and run a company. It's the same. Okay. So another long ideality we want to